Hello world, it's Craig. I had a couple of people email me about last week's video on the signals that make this board STD compliant, and interestingly enough, they were both related to the glue logic on the board that I pretty much just skipped over. So I think I need to go back and revisit that glue logic. But I'm going to do a little bit more than that. In this video, I'm going to show you how I come up with glue logic in general while using this board as an example. But there's also a trick I'm going to show you that I use to make sure that the glue logic will stop glitches from getting through to critical parts of the circuit, especially edge-sensitive latches. We have this output port on this board that is clocked with a rising edge, and we need to make sure that that doesn't get any glitches, or it'll latch whatever crap happens to be on the data bus. It isn't really a trick, it's just a fundamental knowledge, but the way that I like to think of it really helps speed up reading schematics. It helps with circuit understanding, and it helps prevent hardware bugs from sneaking into my circuits. If you aren't familiar with the term by glue logic, I mean the miscellaneous gates in the circuit that determine when the big things happen. On this board, I'd say there's three sets of glue logic. The first is the socket chip select that selects which of the memory sockets is going to be selected. The second is the decoding that latches data to the onboard output port, and I think that's probably the most critical one as far as glitches are concerned. And the third is the logic that controls the direction of the transceiver on the data bus going out to the STD bus. Now, all of the latches, the buffers, transceivers, they're key elements, and I may colloquially refer to them as glue, but I don't really mean it. These are all pretty much key elements, and they're not just glue logic. Now, keep in mind, this is just the process that I use to create glue logic. I'd expect that there are better tools and techniques and people that already know this, and this is child's play for them. And these little bits of glue logic are simple enough that I'm going to use diagram techniques and not Boolean equations. I'm not sure if you're disappointed or relieved about that. I prefer to use diagrams whenever I can because I can still figure them out after long stretches of not using them. But whenever I need to use Boolean equations to solve circuits, I have to re-educate myself nearly every time, which, as they say, is evidence, I guess, that I never really learned it in the first place. Of these three bits of glue, the one that is the simplest and the least critical is the onboard memory enable. So let's do that first. I generally do this on paper, but to speed up the process and to make the circuits cleaner and easier to see, I'm going to try using KiCad to recreate what I did before. I would guess there's better tools than either paper or KiCad. Let us know if you have a favorite. I'm always looking for better ways of doing things. If I knew I was going to do this video, I would have kept the circuit diagrams I drew earlier rather than throwing them in the recycle bin, but it isn't a big deal to recreate them. It should be fairly useful, and it gives me another chance to recheck my work without the bias of remembering what I did before. So here it goes. I have a blank KiCad schematic here. I've brought in a few little gates that I know I'm going to need, and the first thing I'm going to do is write a description. I start with the simplest description and the simplest logic diagram I can think of. Sometimes I need to do a truth table or start with a K-map, but I'm going to go directly to a diagram here. So let me write a little description and come back. This is for the memory chip enable glue. It needs to enable the memory chip whenever the processor is in a memory cycle and when the memory decoder has mapped the address to this chip's block of memory. Now, from my description, I'm going to create a little circuit diagram for this. So I want to enable the chip whenever we're in a memory cycle and the memory block is decoded. So I know already I'm going to need a couple of input signals. I'm going to copy this. I'm going to assign signals to these whenever a memory cycle. So I need to be in a memory cycle and whenever our memory block is decoded. So I'm going to do this for M1 right now, and I'm going to say that M1 is decoded. Okay, that's pretty simple. All I need to do is AND those two together. That's going to give me an output, and that output is that M1 is enabled. So I have two habits when I draw these diagrams. The first is that I use assertion level logic. And the second is that I use functional rather than actual signal names. By assertion level logic, I mean that when I write down a signal name, in this case, like memory cycle, I'm implying that that signal is true when it's asserted. So that line memory cycle goes true whenever we're in a memory cycle. And just like M1 decoded goes true whenever M1 has been decoded by the address decoder. And the output of this, M1 enabled, will go true when it's time to enable that chip. And these are all functional signals. I mean, I imagine the signals that do what I need them to do rather than actual signals. I'll create these functional signals from actual signals after I'm sure I have the correct logic in this first step. If I try to use actual board signals during this first step, it does a couple of things. One is that it just makes it a little bit more confusing because some things are active low, other things are active high, and the other is it makes it processor dependent. So I just use these functional signals, positive assertion level, as my first step, and then I convince myself that this circuit is right, and then I will flush this thing out and get all the details put in. So now that I have it, let's do that second step. Let's actually convert these into actual board signals. So I'm going to make a copy of this so I can watch my progress here. I look around the board and I see what I have that's available or what I can create to get these signals to assert with positive logic. The functional signal M1 decoded will be asserted whenever the decoder selects the first memory socket, this M1 socket. If we actually look on the board, this M1 decode goes low whenever the 74156 sees that socket's address. So to create the asserted signal in my diagram, I only need to invert that M1 decode signal. So let me grab an inverter, M1 decode, all I need to do is invert that, and I know on the board it's called M1 decode, but I'm going to simplify that a little bit. I'm just going to call that, it's an active low M1. All right, the name of this signal hasn't changed here. This is still M1 decoded, but I take M1, I invert it, and I get my functional M1 decoded. And likewise, the IOM signal on the board is high for an IO cycle and it's low for a memory cycle. So I just need to invert IOM to create a positive assertion signal that tells me that we're in a memory cycle. Okay, so I'm just going to copy that, and this guy is just IOM. Now the output signal to the memory device itself needs to be asserted low since the chip enables on the memory devices are all active low. So when M1 is decoded and when it's a memory cycle, the output of our AND gate will go high. I need to invert that because my actual board signal is active low M1 chip enable. So I'm going to grab another inverter and put on the output. And this output I'm going to call it's active low M1 chip enable, and that's the actual signal on the board. The functional signals have now been converted to actual board signals, and that gives me the 0th version of that glue logic. And you can see that if I have a bunch of spare AND gates and a few spare inverters, this may be the preferred configuration for that logic. But with those inverters and the inputs and the outputs, it cries out to be demorganized where it becomes an OR gate. So let me demorganize that, make that into an OR gate. You're going to copy this, paste it, and then demorganize it. Here you can see I've just demorganized it. Now I need to expand this to include all 3 memory chips. And for later, count up the number of each gate and make a little note by this diagram how many gates I'm using. So I've done that. I've expanded it. I've called this number 0. And I have over here a little register of what I've got. I've got no inverters, I have 3 OR gates, and I have no AND gates. So I'm going to do that for all of the versions I make for all my circuits. So I can come back and later we have to package these into devices. You can imagine a case where there's a couple of leftover OR gates and one leftover AND gate, in which case I may need to come back, do some more iterations of this circuit to use up leftovers. But for now, this will do. I just keep in mind that I can demorganize back any of these to an AND gate if it makes things fit better in the end. Okay, so enough of that one. Let's go on to the onboard port latch, which I think is the most critical one on this board. All right, I've already written down a little description here for the onboard port glue. So for the onboard port, and this is all just assertion level functional signals, we want to latch on the trailing edge of the data valid strobe only when IO is true and this port is decoded. And we're going to use that signal as a clock into our data latch, so glitching is unacceptable. We must ignore IOM and decode transients until we get the data valid signal. So let me draw that as a circuit diagram. Again, it's pretty simple, and I'm going to talk about this second device here in a second, but let's look at the first part. We only want to latch the flip-flops if we are in an IO cycle. So I have this IO access. We need to be in an IO access cycle. and not a memory cycle, and if the address decoder has selected this port. Okay, so I'm just going to AND together that we're in an IO cycle and that our port is decoded, and I'm going to create this signal that's going to be port selected. So when port selected is asserted, so when that goes high, it means that our port has been selected. It's critically important that we block that signal until we receive a data valid signal. So I put in this gating device, and for dramatic effect, I just represented it as this nondescript box. It has an output enable and a data input. The truth table looks like this. When the enable is false, the output goes false no matter what the data input is. When the enable is true, the input is simply transferred to the output. And in our circuit, we'll use that to block any glitches that are on the port select signal, since the output will be disabled and held at 0 until the glitches have all stopped and the data valid signal goes true. And we know there's going to be a lot of glitches on that port select signal, since the decoder output will be hitting random values. It'll be seeing all these address transitions come in, and the address will be changing. We'll be getting random enables, and that all needs to propagate through, stabilize, settle down. And each of those transients will change the port selected state. And since we're going to use that in an edge-triggered flip-flop on the port, each of those glitches would latch bogus data into our onboard port. If it were just LEDs and speaker, there'd be no problem, but that port controls which memory map we're using, so randomly changing that memory map would be a major bug in this hardware. Now, once we receive the data valid signal, so that's asserted, then we can allow the port selected signal to pass through this gating device. So the question is, this is not a magical device. What device has this truth table? If the enable input is false, the output is logic false. If the enable input is true, the output just follows the data input. The reason I'm being overly dramatic here is the same reason I pointed out in my video on the mystical, magical, exclusive OR gate. In that video, I explained how reading schematics with an exclusive OR can be so much simpler and easier if you figure out the intended function of the exclusive OR rather than focusing on the logic levels. Once you see they're just using an exclusive OR, for example, as an adder or as a programmable inverter or as a quality detector. So if it's a programmable inverter, you don't need to keep figuring out the logic that's going into this gate. You just say to yourself, this is the enable invert input, and this is the data. And anytime this invert signal is asserted, that data line is going to be inverted. And it saves you from having to go back every time and say, okay, well, if this is 0 and this is 1 and 0, 0, 0, 1, it makes reading the schematic trivial if you think about the purpose of that gate rather than it just being a logic device. And this is the exact same thing here. This gating device that I have is just an AND gate, with one input being the enable and the other being the data. But if I treat this as a gating device, meaning it either lets the data through or not, then I don't have to repeat and go through logic values for every condition. When I get to this gate, I just say to myself, this is the enable input. When it's true, whatever is on the data input passes through. When the enable input is false, then the output is false. So I'm just going to redraw this with an AND gate. My word of advice is this. Look for what I call the superior signal in the circuit. In this case, the superior signal would be the data valid signal, because we don't care what any of the other signals are until the superior signal goes true. Once it goes true, then I only have to work and rework the inferior circuit logic states, so this little AND gate here, since I know they will just pass through the gating device whenever that data valid is true. And if the data valid is not asserted, then nothing's going to get through that gate. It's just going to go to 0. And the superior signal may be an enable to an output or act as a gating device like this. It may be a clock to a latch, or as in the case of the exclusive OR, it may be the defining the equality reference or serving as the invert control line. But look for the superior signal and conceptually what it's doing to that gate. Where this signal meets the others, make a notice to its function. If you don't already do something similar, I guarantee you that this technique will improve your schematic abilities. It'll make reading schematics faster. It'll help reduce hardware bugs. And for me, this is especially useful when I'm doing hardware diagnostics, because when you're doing diagnostics, you're going back over the same part of the circuit over and over again with different input states. And you have to go through and figure out, what the logic level is going to be through each device under each condition. But if I back up and I look at the forest rather than looking at each tree, it really speeds up the diagnostics. And no doubt some of you are going to poo-poo this idea, but if you find it useful, please let me know in the comments. Now back to our glue logic. As it's drawn, I have the second gate, which is our final gating device. And this, of course, is just a 3-input AND gate. And I could have drawn it as an AND gate, a 3-input AND gate from the very beginning. But in my mind, it helps if I can see it as the gating device and if I can label the intermediate signals. So this is where we are. Again, these are still just functional signals. They're not connected to actual board signals. So that's our next step. As I mentioned, one advantage of using functional signals is that this circuit is still processor independent, and it's not tied to any specific logic levels or timing or actual signal names. But it's time to assign actual signals, and let's look at the data valid strobe first and look at the port output timing diagram for the 8085. The last step in a port output is the write strobe. On the 8085, this line is normally high, and when the data is put onto the bus, it goes low. But the data is not actually guaranteed to be valid until the rising edge of the write strobe. To get the 8085 active low write to match our data valid signal, we need to do an invert on that signal before it comes in. So I'm going to drop an inverter on this input. The signal name into the second AND gate is going to be the same, but the signal name on this inverted input is actually just going to be the 8085 write signal. And that's the actual signal on our board. Let's switch over and look at the output of this next. The flip-flop I use is the 74-273 that will latch on a low to high transition. But when the data valid goes true, and it allows the port selected signal to pass through the gate, if that port selected is true, the output will see a low to high transition that would latch our flip-flop. So as soon as that data valid signal went out, leading edge of that data valid signal, it would latch our flip-flop. And we don't want that low to high transition to come first, we want it to come last, meaning when this data valid signal goes back low at the end of the strobe, the output of the gate needs to then go high. So that tells us that we need to add an inverter on this output. So let me drop an inverter there. Now this output is the real board signal, not just the functional signal I used in the description. And as a reminder that the transition is actually important, I'm going to put a little waveform on this label name showing me that what I already figured out once, so I don't have to figure it out again, that this is going to have a strobe with the rising latch on the trailing edge. Let's go back and finish up the inputs. We can assert the I/O access signal using the IOM directly, since when the IOM is high, we're in an I/O cycle. So let me clean this input up, and all I need to do is add the name, the signal name IOM to this I/O access line. So that line is the IOM, and our previous name, our functional name, was I/O access. But the address decoder, just like before, it's going to take each of its outputs low when it's asserted. So we need to invert that port decoded in order to get this positive assertion level signal high. That should be it. We now have real board signals. So our write strobe, our output board, our onboard port signal tells us when our onboard port is selected, and our IOM, and then our output is this negative going strobe into our data latch. Let's look at the timing diagram, walk through this one more time before we start simplifying. The I/O and the inverted onboard port create the port select signal. True if this port is selected during a port machine cycle, false otherwise. Okay, so that first gate looks like what we want. When the write strobe comes, it goes low, making the data valid high and passing through whatever state the port selected is. And then when the write goes back high, the second gate is disabled and the output falls low. The final output is inverted, so our final output gives us this low to high transition that we need for the latch. And I know that AND gate, the second AND gate, just passes through whatever the port selected signal is, so I don't need to go back through all that logic with each of the possibilities of those inputs. I think we're done with that circuit. All of these signals are actual board signals. I think this circuit is correct. And again, if we had a couple of AND gates and some inverters, we could use this circuit just the way it is. So I'm going to go ahead and put a version or a circuit number on this, and do a count of the gates that are in that circuit so I can to help package them later. I've done that. I actually made a copy of it. I restored the last version to the way it was. I've given this version number 0. Cleaned it up. We've got 3 inverters, no OR gates, and 2 AND gates. Now eventually we're going to need to be combining all of these glue gates into packages. So it'll be useful to see the different variations of the same functional logic, but using the various gates. So my next step is to just start distributing and demorganizing things to swap ANDs and ORs, combining signals, and adding or eliminating inverters. By demorganizing, I mean applying De Morgan's theorem and inverting the inputs and the outputs to allow the gate to be flipped between the AND gate and the OR gate. Let me demorganize the second AND gate. So I'm going to make a copy of this. Okay, so that's been demorganized. Now I'm just going to simplify that by getting rid of both of these, and I have to get rid of this label in here because that label is actually, or that signal is gone. That just becomes the right line. These are gone. That just becomes my latch signal. All right, and this has now 2 inverters, 1 OR gate, and 1 AND gate. And this is version number 1. Let me demorganize the other AND gate, so then I'll have all 3 versions. I'll have a version with 2 AND gates, 2 OR gates, and 1 of each. These are my 3 versions. For now, that looks like enough options. When I'm picking the final design, just like the other one, this circuit's pretty flexible since it can use any combination of leftovers. 2 ANDs, 1 of each, or 2 ORs. After I do the last piece of glue logic, if I need to, I can come back and I can add other variations of this equivalent circuit. I think it's worth looking at this, and also this applies to the last piece of glue logic we did. But the AND gate serves as a gating device for positive assertion signals. Likewise, the OR gate serves as the gating device for negative assertion signals. So if you just keep that in mind, it helps having to refigure that out every time. Now on the last glue for the enables of the memory blocks, we didn't need to use a final read or write gating device since we aren't worried about glitches on its output, because internally those devices will use the read or write signals as their superior gating signal to get rid of any glitches. If those devices didn't use that data valid signal or the read or the write line, then we would have needed to be more careful to make sure that we didn't get glitches out of ours, just like we did on the onboard port latch. Now let's finish up by looking at the transceiver glue requirements. For the bus transceiver glue, we need to drive data onto the STD bus unless we're in an offboard read cycle or if the interrupt acknowledge is asserted. Now glitches aren't critical in this circuit, but nonetheless we don't needlessly want to create glitches because they will generate transients on the STD backplane by flipping that transceiver back and forth with every transient that propagates through the machine cycle. While it's not critical to use the read or write strobe as the final gate, I think it's still a good idea, and as luck would have it, the read strobe shows up in the design anyway, but for certain it's not as critical as it was for the onboard port. Let me convert that description into a little circuit. This isn't done, this is just the first step. The first stage ANDs a not onboard signal with the read cycle to create an offboard read signal. So this offboard read will be asserted whenever we're in a read cycle that comes from offboard data. And we know we're going to have this receive signal because this is what's going to tell our transceiver whether it needs to be in receive or in transmit. So we know that that's our end goal, but we also have to OR that offboard read with the interrupt acknowledge, because we have to receive anytime that we're doing an offboard read, or if the interrupt acknowledge, because that interrupt acknowledge is how somebody else can jam a signal onto the bus. So let me put in an OR gate for those 2 signals. In this diagram, whenever it's an offboard read or the interrupt acknowledge is asserted, this receive will be asserted. Now the interrupt acknowledge, if you're not that familiar with it, it happens whenever the processor has relinquished the bus so another device can jam in an opcode. So in either case, either an offboard read or interrupt acknowledge, the offboard device will be driving the data bus of the 8085, so that transceiver needs to be in the receive mode. Any other time it can be in the output mode. And just as before, these are all assertion level signals, and they're just functional signals. They're not the actual real signals. The first thing I'm going to do is figure out what this functional not onboard signal is. Let me copy this so I can manipulate it and figure out what this not onboard signal is. Well, I know that each memory device has an enable signal. So let me create an enable signal for each of these memory devices. I have those 4 memory enables. If I OR those together, then if any of these memory enables are asserted, this output will be asserted, and that will be my onboard signal. So I'm going to create this as an onboard signal. All right, if that's my onboard signal, if we invert that, we, by definition, will get a not onboard signal, which is exactly what I needed for my little functional signal over here. So let me grab an inverter and invert that onboard signal. So if any of these 4 memory sockets are enabled, and M4 is like the little 1K, the one that was further split down into 1K blocks. If any of those are enabled or asserted, this onboard will be asserted, and so not onboard will be deasserted. If none of these are asserted, these are all low, onboard is false, and so not onboard will become true. Okay, so this part of the circuit I think is right. For the 8085 read cycle, just like before, we're going to use the read, but the read is active low, and this read cycle that I have in my little diagram here is active high, so I need to invert that. So let me do that just like we did before. Let me copy that inverter, and that is just the read signal. As long as we're not in an interrupt acknowledge signal, so this down here is going to be false. Whatever not onboard is when the read cycle is asserted, or during the going low read strobe, it will let the not onboard go through this gate and into this OR gate. So receive follows this offboard signal. Now, if the interrupt acknowledge is asserted already, then the receive is already asserted, and so it will stay asserted, and there shouldn't be a glitch in that. So there's still a couple of inversions we have to do here. The first is that these M1 through M4 assertion level signals are the opposite of what I have on the board, since the 74156 decoder takes its output low. So I need to invert all of these inputs before I can attach them to actual board signals. So let me put in inverters on all of those inputs. The other thing is the interrupt acknowledge signal from the 8085 is asserted low, so I need to drop an inverter on that interrupt acknowledge as well. The logic of the receive output matches the receive not send on the board, so I just need to add a name to that signal. This gives me the first usable circuit since all of the signal names are actual board signal names. I had to change this bottom one. This is actually the 8155 chip enable. Now to reduce, simplify, and make equivalent versions with different gates for final packaging. First thing, it seems pretty unlikely that I'm going to need another 4-input OR gate, and those come as duals. So it makes sense to demorganize that into an AND gate, giving me option number 1, because I possibly could use a 4-input AND somewhere else. So I'm going to demorganize that OR gate, give me the next version. So I demorganize that AND into an OR, and it seems almost as unlikely that I'll need another 4-input AND gate. So I'm going to split that into more versatile 2-input AND gates since I can use those anywhere. Let me do that and create version 2. As before, I list the number of inverters, OR gates, AND gates, and then oddballs like that 4-input AND gate. I needed one of those. So I just like to create the most obvious option so I can look at the whole picture. I'm now going to demorganize the first AND gate, so I've got 2 OR gates. The next step, I'm going to go back to number 2 and demorganize the OR gate, so I've got 2 AND gates as well as the 3 out front. So let me make it so that they're all AND gates. It's going to duplicate in terms of the number of gates, but it's going to be a little bit different order. It might connect better on the final board. Let me just take 2 again, but swap the AND and OR around, making version number 4, or making version number 5. So yeah, 2 and 5 are essentially the same. It's just a different order of those gates, but it's done now. Let me get rid of that OR gate. If I start replacing the ORs with an inverter with NORs and the same with the AND gates, I'm not sure I'll be able to use the entire quad package, but let me go ahead and make those versions just so that I have them noted here. Now those are done. What eventually happens is I find that I'm demorganized the circuit back into its original version. So I know it's about time to stop. So eventually I'll reach, diminishing returns on swapping these things around. Now what I do is I look over these options, and we need to package these into the devices that we can get, the 7400 devices that we can get. So I need to go through and pick one from each column that tend to complement each other. For example, if I take option 4 from this first column, make a copy of that, and option 2 from the second column, and then my option 0, my only option that I have so far in the third column, if I create the total, I need to have 4 inverters, 5 OR gates, and 5 AND gates, right? 3. So 4 inverters, 5 OR gates, and 5 AND gates. So obviously, that's not a good choice because that would leave, that's only using a quarter of each an OR and an AND. So I can probably fill something out better. But this is, so this is 2, 4, 5 chips it would take to do that combination. Let me do better. Let me take option 5. I want to get rid of one of those OR gates or AND gates. Just get rid of somebody so that it drops down that one extra straggler chip. And option 2, option 0. So option 5, 2, and 0, now I only need 3 inverters. I need 6 OR gates, so that's 1.5 chips for that, but I only need 1 quad 2-input AND. So that's 2, 3, 4 chips. Rather than having 2 OR gates left over, I can do the same thing, but have either 2 AND gates left over, or I could have one of each left over, 1 OR gate and 1 AND gate. So let me make those 2 combinations. These are what I think are the 3 likely candidates. Now I've got this one down here that has given me 2 extra OR gates. This one just to its right gives me 1 extra OR and 1 extra AND, and then the one above that gives me 2 extra AND gates. Now the schematic that I have posted now, I have the extra OR gates. So I used the 5-2-0 combination, the schematic that I have posted now. I've already started laying out the board, so I'm not sure I'm going to go back and change it because this one that gives us one of each extra gate is a little bit more flexible, because if somebody wants to come back and make patches on the board or use those in the little sandbox area, it gives them 1 AND gate and 1 OR gate to play with. So this little 0-4-0 option has that little advantage of giving the extra gates, one of each gate to play with. But like I said, I've already started laying this board out. I'm not sure I'm going to go back and make that change. I think I really like doing this in KiCad rather than on paper. It makes it much cleaner, and I think I'll do it that way from now on. Plus, I get to keep a copy of this and these options that I made with the other board files, so it'll help later if I did something wrong and I need to fix something on the board. I can go through what my thinking was, because I just don't tend to keep paper around. I tend to just throw that in recycling. Now hopefully this video has had some useful information, and maybe it'll help you out when you're creating your own glue logic for your boards, or if you're working through somebody else's designs, or when you're doing diagnostics on hardware. I particularly like that technique when I'm doing diagnostics because it just saves from having to get bogged down in doing logic states over and over and over again. Well, thanks for watching. As always, Okay, we interrupt this sign off for this newest, latest information. And this is interesting. I played with those glue logic combinations quite a bit several weeks ago when I was designing the board. But I was doing it all on paper and, while watching TV, that kind of thing. But just now, when I was editing this video, adding the whiz-bang arrows and the animations and so forth, I noticed an even better choice than the ones I have in the schematics. And it's even better than the last option that had the extra AND gate and the extra OR gate, because unless I've made a mistake, this new best option eliminates an entire logic chip. So it drops the number of glue chips from 4 down to 3 chips, and I completely overlooked that version before. Let me know if you see it. This shows the value of stepping away from a design for a while and then picking it up later when you've forgotten most of what you've done. I'm further along with the layout than I was when I saw the last better version of the glue, so I'm not sure if I will change over to this one or not. I have to undo quite a bit of the board, but it's pretty tempting since it eliminates an entire chip, and I think future me will be impressed that old me was able to do the glue logic so nicely. So we'll see what I do. I guess the message is to watch for updated schematics to see which way I go on that. Well, thanks for watching. As always, this channel is entirely fueled by likes, sharing with others, subscribers, and engaging comments. I will talk with you later. Bye-bye.